Part 4, Logarithmic and Exponential Equations and Applications. When solving logarithmic problems, conversions between logarithmic equations and exponential equations may be required. In the previous section or chapter, some exponential equations couldn't be solved algebraically as the bases could not be made the same. This is no longer an issue as logarithms can be used. Okay, so one of the handy skills that we're going to use when we solve equations like this is to take the log of both sides of the equation. Okay, so for example 1, if I take the log, so we go log 4 to the x equals log 5 to the x minus 2. Okay, so when we do that, so we take the log of both sides. Now remember, in laws of logarithms, these exponents can jump down in front. Okay, so you're going to get x log 4 equals x minus 2 log 5. Now remember, we want to try and get the x's onto one side of the equation. That's how algebra works, right? So this log 5 is just a number, so that can distribute to both of those pieces. So we get x log 4 equals x log 5 minus 2 log 5. Okay, not a big deal. Okay, so now we're going to want to move this log over. Okay, not a problem. So we go x log 4 minus x log 5, okay, equals negative 2 log 5. Now, here's we do this so often in algebra. It's just, it looks different when there's these log things. Each term has an x in it, so we can factor that out. So log 4 minus log 5. Okay, so that's a negative 2 log 5. Okay, and then we just divide by log 4 minus log 5. Okay, whatever you do to one side, you do the other. So log 4 minus log 5. Okay, so that, of course, equals x. So that is the exact answer, and these things do come up on the diploma exam. Now, so that is the, like I said, the exact version. If you type that into your calculator just as is, you can get a decimal approximation, and that's just it. I've seen them both on diploma exams and, of course, the unit exams, etc. So you will have to be able to do the exact form, and you'll have to be able to do the decimal as well. So if you type that in, let's go to 3 decimal places. That would be 14.425. Okay, so that is the value of x. Awesome. So let's try the same thing for b. Okay, so we take the log of both sides. Okay, so we go log 2 times 3x plus 4, okay, equals log 7 to the x over 2. Okay, awesome. Now, before we can just start rearranging like the last one, we have to notice that this part is a product. The 2 is multiplying the part in the brackets. So we actually have to separate that first. So that's going to be log 2 plus log 3 to the x plus 4. There we go. Equals log 7 to the x over 2. Okay, great. So now that we've separated the log 2 and the log 3 to the x plus 4, now we can do some more of the log laws. So these two exponents will jump down in front. So log 2 plus x plus 4 log 3 equals x over 2 log 7. Okay, so again, we're going to distribute the log 3 into the x and into the 4. So log 2 equals, plus x log 3 plus 4 log 3 equals x over 2 log 7. Okay, great. So now, of course, we want the x's on the same side. So we're going to take this x and move it over. So minus x log 3. So we're going to get log 2 plus 4 log 3 equals x over 2 log 7 minus x log 3. Wow, that's intense. I know these are tricky, but nothing in here is really hard yet. It's just, it looks a little different. Okay, so we can factor the x out again. So x, and then that of course turns into a 1/2, right? X divided by x is 1, so the numerator there is 1. So 1/2 log 7 minus log 3. Okay, and that equals this other part, so log 2 plus 4 log 3. Okay, and then just divide. 1/2 log 7 minus log 3. 1/2 log 7 minus log 3. Okay, so that's what equals x. So that is the exact answer. Okay, if we want to the nearest, let's go thousandth again. Okay, so we type that into our calculator, and we end up with negative 40.488. So that is the value of x. So the keys there, we took the log of both sides. We used the laws of logarithms to expand out the individual logs. We got the x variables isolated on one side of the equation, then we factored them out and solved for x. Awesome. Okay, so then example 2. Okay, so solve the following. Log base 4 of 5x plus 1 equals log base 4 of x plus 17. Okay, well, if the logs are exactly the same on both sides, okay, they just cancel. So that's kind of a nice thing. So that all that means then is 5x plus 1 equals x plus 17. That only works when the two logs here are the same base, and of course in this case they are. So that's great. So minus x, minus 1 minus 1, so we get 4x equals 16, so x equals 4. Now, one other consideration we have to have for these. Remember, the argument for logs can never be negatives. So that means that this 5x plus 1 has to be bigger than 0. 5x plus 1 has to be bigger than 0. So minus 1, so 5x has to be bigger than negative 1. So x has to be bigger than negative 1/5. Okay, so that is the restriction, at least for the first part. So we have to do the restriction on the next part as well. So, so the x plus 17 also has to be bigger than 0. So x has to be bigger than negative 17. Okay, so if you look at that, x is 4. It satisfies both of those. Now, really, the domain on this is going to be this one, because if you're bigger than negative 1/5, you are also bigger than negative 17. Okay, so, and of course, our value, x is 4, is bigger than negative 1/5, so that will work. Okay, let's try this next one, because this gets a little weird. Okay, so we combine the two logs. They're subtracting, so this is going to be log, okay, and then 5x over x minus 1, okay, and that's supposed to equal 1. Now, where do we go from here? Remember, this is base 10. So, and logs solve for exponents. So once I have the single log here, this 1 is an exponent. So 10 to the 1 equals 5x over x minus 1. Nice. Okay, so then the log is gone. We don't have to deal with it. And we just multiply that up. So we get 10x minus 1 equals 5x. So that is 10x minus 10 equals 5x. Okay, tell you what, we'll go minus 10x minus 10x. So negative 10 equals negative 5x. So x equals positive 2. Okay, so that's our answer. Now in here, so we can't be 0, so x has to be bigger than 0. And for x minus 1 also has to be bigger than 0. Okay, so x has to be bigger than plus 1. Okay, well, 2 is bigger than plus 1, so we are in the correct domain, so this is going to work just fine. Okay, the last one for this page. Okay, so again, we have 2 logs that are subtracting, so we're going to end up with 1 log base 6 of x minus 3 divided by x plus 6 equaling 2. Okay, so what ends up happening here, so remember, log solve for exponent, so the 2 is an exponent on the base 6. So 6 to the 2, which is 36, okay, equals x minus 3 over x plus 6. Okay, and then we just solve this. Okay, so that multiplies up. So 36x, let's see, 36 times 6 is 216. So plus, wow, I messed that number up, didn't I? Okay, so 36 times 6 is 216 equals x minus 3. Okay, so let's see, minus x, so we're going to get 35x. Okay, and then minus 216. Whoa, sorry, I'm getting awful close to the button there. Minus 216, there we go. Okay, and that's going to be negative 219. So x is negative 219 over 35. Wow. Okay, that's a very large negative number. Let's see, as a decimal, negative 219 over 35, okay, is negative 6.26. Now let's check the restrictions on here. So x minus 3 has to be bigger than 0, so x has to be bigger than 3. Okay, and then x plus 6 has to be bigger than 0. X plus 6 bigger than 0, so x has to be bigger than negative 6. Okay, now the thing is, we have to go with the smallest restriction, so x has to be bigger than 3. We notice our answer of negative 6.26 is not bigger than 3, so this is extraneous. So if that's extraneous, there is no solution here. Interesting. Okay, variations on these questions. If this was a plus sign, then we would get x minus 3 times x plus 6. Okay, and then that would be a quadratic, and then you would have to solve that quadratic equation. It's not a big deal, it's just one of the variations that you will see. All right, applications. So there's lots of applications of logarithmic scales and exponential scales. One of them is the pH scale. Now, if you've taken some chemistry, you know a little bit about this. pH is the measure of the concentration of hydrogen ions, so H plus aqueous. Okay, and the concentration in chemistry is these square brackets. Okay, so the concentration of H plus in a solution. The greater the concentration of hydrogen ions, the lower the pH. pHs between 0 and 7 are acids. A pH of 7 is neutral, and a pH between 7 and 14 is a basic solution. So pH can be found using this formula. So pH is the negative log of the hydrogen concentration. Now, if we turn this back into exponential form, so divide by the negative, so negative pH equals log of the H. Okay, H plus, I guess. Okay, so remember, this is base 10, so 10 to the negative pH is going to be our H plus concentration. Now, we can write the aqueous sign if we really want. If you were in chemistry class, then yes, you would have to write that, but now it's up to you. Okay, so 10 to the negative pH is the hydrogen concentration. So we're going to be using both of these equations, and let's figure out what we're trying to do. So example 1. In spring, the pH of the water in a mountain stream is 4.2. So quite acidic. Okay, it is 90.5 times more acidic than the water in the fall. Okay, determine the pH of the water in the fall. Okay, so in the spring, we are really acidic. In the fall, we're not quite so much. Okay, so just to get a handle on these things, if I'm less acidic in the fall, the pH should be higher. Okay, so it's a nice little just connection to make, because you can kind of check your answers later. Because if you get a pH of less than 4.2, you are more acidic, and you've messed it up somewhere. Okay, so tell you what, if the pH of the water is 4.2 in spring, okay, and that is 90.5 times more acidic, we can write it like this. The H plus concentration in the spring equals 90.5 times the H plus concentration in the fall, right? You have to take the H plus in the fall, times it by 90.5 to get the same concentration in the spring. Well, tell you what, let's figure out what the concentration is in the spring. So the H plus, okay, so H plus equals 10 to the negative pH. Well, the pH in spring is 4.2. Okay, so how strong is that? Okay, well, when you figure that out, okay, 10 to the negative 4.2, 10 to the negative 4.2, so that has a concentration of 6.3 times 10 to the negative 5. Okay, so that is what the concentration of H plus is in the spring. And remember, that equals 90.5 times the H plus concentration in the fall. Okay, so then we divide by 90.5, divide by 90.5. Okay, so 6.3 divided by 90.5. So the H plus in the fall, is equal to, okay, so 6.97 times 10 to the negative 7. Okay, so that's the hydrogen ion concentration. Okay, we want to turn that into a pH. So remember, pH equals the negative log of the H plus. Okay, so in the fall, that's going to be negative log of 6.97 times 10 to the negative 7. So the pH in the fall is going to be 6.2. Awesome. Okay. So the main point about the pH scale is we want to always convert it back to the H positive ions, the hydrogen ions, okay, because then we multiply those or divide them 90.5 times, bigger, smaller. So we always want to work with the H plus. Okay, example 2, or the next application, is the Richter scale. So the Richter scale is a logarithmic scale used to describe the relative strengths of earthquakes. The formula for determining the magnitude of an earthquake is this. Magnitude equals log of I over I0, where M is the magnitude of the earthquake, I is the intensity of the earthquake, and I0 is the minimum intensity an earthquake can have. Okay, so think of it this way. Right now, the ground is shaking. Okay, we can't tell because we're used to it, and it is so small that we can't tell. So I0 is just what the Earth does. Okay, so that's like the baseline. So if you hooked up one of those meters, like the seismograph, you know, the thing that goes, see them on all the movies. Okay, if you see one of those and you just hooked it up right now, no earthquake going on, it would just be a little twitter. Okay, so that would be the I0, just how much the ground is moving normally. Okay, and really what's going to happen is the I0 is going to cancel out almost all the time. So I'll show you that here in the examples. Now, if I convert this to an exponential equation, remember the log is base 10. So this is 10 to the magnitude equals the intensity of the earthquake divided by that base intensity. So we can use both versions of this. Okay, so let's flip the page, and look at our example. So the strongest earthquake in Alberta is 4.4. How much stronger is the strongest earthquake in the world if it was measured at 9.5? Oh, okay. So here's the idea. The magnitude or the strength of the earthquake. Okay, so we know, here I'll write down that formula so we don't have to, so the magnitude was log I over I0. Okay, so I'm saying that the magnitude was 4.4. Okay, well remember, if we convert that, 10 to the m equals I over I0. Okay, so just how intense was this Alberta earthquake? Okay, so the Alberta earthquake was 4.4, so 10 to the 4.4, okay, equals I over I0. Okay, so really, I guess I would be 10 to the 4.4 times I0. Okay, so that's how intense the Alberta earthquake was. Okay, and we could figure that out. 10 to the 4.4 is, well, let's just figure it out really quick. It's not important because we're not going to use that, but it's 25,118. Okay, so that sounds like it's really intense. Sounds like it. Okay, now, here's the thing though. The intensity of the world earthquake, okay, here, let's set that up proper. Okay, so 10 to the magnitude, so 10 to the 9.5 is equal to that earthquake's intensity over I0. Okay, so if I want to compare the two, so let's see, the intensity, let's call that the world one, and then IA for the Alberta one. Okay, so the intensity of the world one is I0 times 10 to the 9.5. So if I want to compare these two earthquakes, really I just divide the intensity. So IW divided by I Alberta. And that'll give us how intense, or how many times more intense the world one was. Okay, so this is going to be 10 here. So 10 to the 9.5 times the base intensity. The Alberta earthquake was 10 to the 4.4 times the base intensity. See what I mean? The base intensities just cancel out. So that's cool. Now look, this is just a glorified exponent law question. They're same bases, and we subtract the exponents. So the difference, or the how many times greater the world one was, is simply 10 to the 9.5 minus 4.4, which is 10 to the 5.1. Okay, well, if you type that in, 10 to the 5.1 equals 125,893-ish, and rounded to the nearest whole number. Okay, so all that means is that the earthquake measured at 9.5 on the Richter scale is 125,893 times bigger than the intensity of the Alberta earthquake. It's really quite incredible. So there you have that one. Okay, decibel levels. Decibels are very similar to the Richter scale. It's just that on the Richter scale, the magnitudes go up by ones. The logarithmic scale for sound is actually on the Bell scale. So a decibel is 1/10 of a bell. It's really not that important. All that is important is when you have, say, 125 decibels, that is 12.5 bells. Okay, so that's going to be what we figure this out on. And it's shown in the equation. Loudness equals 10 times log I over I0. Okay, so what we do is we divide each side by 10. So we divide the loudness by 10. Okay, so loudness over 10 equals log I over I0. And if we convert that back into exponential form, that's 10 to the L over 10 equals I over I0. where I is the intensity of the sound. Okay, so let's look at our example here. Portable music players can produce sounds up to 125 decibels, or 12.5 bells. Any sound above 90 decibels can cause hearing loss if exposure is prolonged. To be safe, experts suggest that the volume does not exceed 60% of the maximum that the player can produce. Assuming your player is, good enough that it can actually produce 125 decibels, how many times louder is this than the recommended setting? Okay, well, tell you what, we got a little bit of work to do. So remember, the only useful way to write a percent is as a decimal, so 0.6, and of the maximum sound level, so is 125, so that is 75 decibels. So that is what they're saying is the what we should be playing our portable music players, like our iPads and iPods, especially if you have the earbuds that you're putting in your ears. Okay, so let's just find out how intense that sound is. Okay, so the intensity of this sound, okay, so I over I0, remember we said was 10 to the loudness over 10, so that's going to be 10 to the 75 over 10, which is 10 to the 7.5. That's how we incorporate the bell scale into the decibels. Okay, so our intensity that we're supposed to listen to is 10 to the 7.5 I0s, right? The I0 just multiplies up. Okay, and the same thing's going to happen as it did in the earthquake one. The I0s are just going to cancel, but okay, let's carry on. Okay, so that is what we're supposed to listen to. The maximum is 125, so the intensity of the maximum is going to be 10 to the L over 10. Okay, well, the loudness is 125 over 10, so that is 10 to the 12.5. So that's the intensity that the portable music player can play. So the I equals 10 to the 12.5 I0s. Okay, we just multiplied the I0 up. Okay, now if I want to compare these things, how many times louder is the maximum? So the maximum, so that's the maximum. This is the recommended. Okay, so we have 10 to the 12.5 I0 over 10 to the 7.5 I0. Okay, well, hey, the I0s just cancel again, and we end up with a nice little exponential again, and we just subtract exponents, so that 12.5 minus 7.5 is 5. So what this means is that the portable music player can play music that is 10 to the 5 times stronger than the experts say is recommended for our ears. Now, just for interest's sake, 10 to the 5 is 100,000. So our music player can play sounds 100 times louder than we're actually supposed to listen to. Crazy, but that's the idea. So we relate everything back to the intensity, just like we did with the earthquakes, and then divide the two to compare the two values. All right, so I need you guys to practice this. Now, this page 400, that was from last section, 8.3. Just, there was some stuff that I wanted to show you in this first before I had you do those questions. Okay, so that's from 8.3. Okay, and then this 4.12, that is from 8.4. Okay, page 412. So I want you to do all of these questions. The pages are ready for you in the workspace card. So go ahead and print those out and do the questions right on there. If you want to use loose leaf, that's just fine. Remember, the answers for these are in the textbook, so go ahead. Now, this was the last section for for chapter 8. So what's coming up next is you will have a formative assessment for all the stuff in Chapter 8. You will have a curriculum review, okay, for Chapter 8. Then you'll have a Chapter 8 quiz. And then you will have the Unit 1, Section 3 exam, which is Chapters 7 and 8. So you have a lot coming up, so you need to study hard. Please ask your teacher any questions you have, or ask me. It's all good. Good luck in the upcoming assessments, and we'll talk with you soon. Thanks.